Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Lin Lau today. Lin has been a productive intern in our team this summer at Microsoft Research. He's also he came a long way this summer across the lake. He's a graduate student in a PhD program in computer science and engineering at the University of Washington, working with Dieter Fox and Henry Kautz, two of our colleagues that we've been collaborating with over the years over at UW-CSE. And Lin has been helping us on some of our smart flow traffic application, machine learning and reasoning this summer. Now he'll be speaking about some work by popular demand from several people who wanted to hear his research at University of Washington on learning and inferring transportation routines from GPS data, among other sources of information. So, Lin.
Thank you, Eric. The topic of this presentation is learning and inferring transportation routines. And so let's imagine we have a user carries a GPS wherever he goes. And we have a system that can observe the GPS measurement all the time. So what kind of system know about the user? So in our paper, we want to show that the system can not only know the location of the user, but also infer the transportation mode of the user, such as the foot, the car, or bus. It can also, given enough training data, predict where the user is going and the most likely path to the goal. Another thing, it can also detect atypical behavior. This atypical behavior could be user errors. For example, the user takes the wrong bus, or it could be intended novel behaviors. So there are a number of applications for these techniques. One example is the customized just-in-time information service. Now there are some information service that can deliver real-time traffic information to mobile devices. But those devices only display the same picture to other people. And most of the information in the picture is not needed for a given user. So using our technique, because we can predict the goal of the user and the likely path, and then you can imagine that then the device can only need to display the traffic information on the predict trajectories. And sometimes it can tell the user some abnormal information around this road. We can use similar techniques for bus information as well. So you can imagine that we display the bus schedule at the right time to a given user. The second application that we are very interested in is a personal guidance system to help the people suffering from cognitive limitations, such as the Alzheimer's patients. So we want to develop a system that can help those Alzheimer's patients move safely through the community. And at the end of this talk, I will give a more concrete example of this in this direction. So here is the big picture of our system. So the input of system includes a sequence of GPS readings and the geographic information system database. Then there are two key components in the system. The first component is the offline learning engine. The offline learning engine uses a long-term GPS sequence and for each user generates a customized probabilistic model. And the second component is called online inference engine. So the inference engine uses a model generated by the learning engine and infer at real time the high-level user activities, such as the user's transportation modes, user's destination, the path to destination, and so on. Before we jump into the details of the components, we want to briefly mention about the two related systems. So the first related system is the GPS. So today, the GPS receivers can be made very small, embedded into the cell phones, the PDAs, or even your watches. And it's very convenient for us to get the GPS signals. And the second related system is the geographic information system. So in our work, we use two kinds of geographic knowledge. The first knowledge is a street map. So we track the user's location on a street map. And the second related knowledge is bus route and bus stops. And this knowledge turns out to be very helpful when we want to distinguish the bus mode with other transportation modes. So in this talk, I will mostly focus on the two parts, the inference part and the unsupervised learning part. I will also briefly discuss how to detect atypical behavior and one application for that called opportunity knocks. So when people talk about GPS-based location tracking, many think it's trivial. But in practice, it's not that trivial. There are many reasons for that. The first, there are many dead or semi-dead zones near the buildings, near the trees, that the receiver of the GPS cannot get enough signals. And the second reason is when people are inside of vehicles, especially bus, usually you can only get very sparse measurements. And there are some other effects, such as multipath propagation, that will affect the GPS accuracy. Also, you may not have very accurate street map. So given those difficulties, how can we do the location tracking robustly? So in our work, we developed a probabilistic graphical model that for the location tracking. The model is expressed using a dynamic Bayesian network. So in this presentation, I want to explain the model from the low level to the high level. So we start with the lowest level. So at the lowest level, we have a sequence of GPS readings. So you can imagine each GPS reading is a point in a two-dimensional space. Then we add more variables. So we want to model the location and the velocity of the user. And because we track the location of the user on a street graph, so the location is expressed as this. So we have an edge on a street graph. Each edge corresponds to a street block. Then we have a velocity along that edge and the position on that edge. So have these three variables, we know the exact location of the user and the velocity of the user. There is another variable, we call it the data association, or edge association. So this variable determines how we can snap a GPS reading from a two-dimensional space onto the street graph. I will explain this variable later in a few slides. So here we have a dynamic Bayesian network. So I will briefly talk about what's a dynamic Bayesian network. So in a dynamic Bayesian network, each node represents random variables. And for some of the nodes, we can observe them directly, such as the GPS readings. And for some of the nodes, we cannot observe them. So they are hidden variables, such as the edge, the velocity of positions, and the data association. And those variables are not independent. So to model the dependencies between the variables, we add the edges between them. So in this case, you can think your current location and velocity depends on your previous location and velocity, right? And also, your GPS reading depends on your current location. So these are some dependencies. And in this dynamic Bayesian network, we have some discrete variables, such as the edge on the street graph. We also have some continuous variables, like velocity and position. So in this hybrid dynamic Bayesian network, how can we do the inference very efficiently? And the techniques we use is called Rao-Blackwellised particle filter. So we start with particle filter. So a particle filter uses a set of weighted particles to approximate the belief at each time. So you can see each particle filter have a set of particles. Each particle have a state and a weight with it. Okay. Then we can reweight the particles based on the likelihood of the measurements. And sometimes we can do resampling. And Rao-Blackwellised particle filter is a kind of particle filter that combines this kind of sampling technique with analytical inference techniques. So each the Rao-Blackwellised particle filter samples some variables and keeps the conditional distribution of other variables given the sampled value. So for instance here, each particle here includes a sampled edge, the velocity at that association. It also keeps the one-dimensional Gaussian distribution of the position. So for each particle, you can think it has a single edge, a single straight block, and a single velocity, and also a single data association. I will explain the last term later. So also each particle has a distribution of the position on that edge. So there are some uncertainties with the position. Because we have this Gaussian assumption, then we can use Kalman filter to update the posterior distribution very efficiently. So here we show how do we do the Kalman filtering on a straight graph. Remember, a Kalman filter uses 2 steps to update the posterior distribution. The first step is called prediction step. So suppose we have this estimate at time k-1. So this red oval indicates the uncertainty of the location, which is a one-dimensional Gaussian. Then at the prediction step, we want to move this estimate forward. In order to do that, we first sample the velocity. After we have the velocity of the user, we move the estimate forward. But when we move to an intersection, we want to know which way to take. We can either go forward or turn left here, right? So we sample the next edge, E. After we sample the velocity and the edge, we know exactly how to move the location estimate before we see any measurements. Then in the second step, we call it a correction step. We want to update the location estimate using the new measurement, GPS measurement. Because we want to restrict the location estimate on a straight graph. So in order to use the Kalman filter, we can project the ZK onto the graph. But there is a data association problem, because we can either project the ZK onto E1 or onto E2. To solve the problem, we sample the data association theta. So if the sampled data association is E1, we just project the ZK onto E1. Then we can use Kalman updates to pull the location estimate upward. The final result is like this. Then if the sampled theta equals E2, we just project the ZK onto E2, and the final location estimate is like this. So this is just one particle. So the whole Rao-Blackwellised particle filter can have hundreds of particles. So in summary, after we sample the edge, the velocity, the data association, we can efficiently use the Kalman filter to update the location estimate. But we not only want to know the location, we also want to know the transportation mode. To do that, we add another variable to the network. It's called transportation mode. So the current transportation mode will affect your velocity and position. Also, the current transportation mode depends on your previous transportation mode and your previous location. For example, if you are close to a bus stop, you are more likely to switch to bus in the next step. Then the key is how do we model the dependencies between the variables? To do that, we encode our prior knowledge. What kind of knowledge? For example, we know different transportation modes have different velocity distribution. The bus and the car have higher velocity than the foot. Also, we know the buses always run on the bus routes. And the user usually only get off the bus near the bus stops. And we also know the user can switch to car only near the car location. So after we encode this prior knowledge into our model, we can potentially differentiate different transportation modes. So when we do inference, for each particle, we add another variable called transportation mode, and we sample the transportation mode. Then we can do the same thing as we showed before to infer the transportation mode and the location and velocity of the user. Here we show a demo of how this works. So in this demo, the user takes the bus home, and we want to infer the location and the transportation mode. So at, this rectangle is a measurement, GPS measurement, and the dots around that is the particles, the location of the particles. Okay, here you can see the color switch from blue to green. This means the system infers that the user gets on the bus. Why the bus is more likely? Because like the switch happens very close to a bus stops. Let's see here. Okay, you can see the color switch from green to blue again. Then the user gets off the bus. You can see there are some very small the circles here, the golden circles here. This is the projection of the GPS measurement on the straight graph. As you can see here, the Kalman filter can pull the particles forward.
The person's sort of walking fast, huh?
What?
The person sort of seems like they're walking very quickly.
This is like a very fast demo.
The bus speed is the same speed as the walking speed.
So yeah, you know, it takes like 10 minutes from the workplace to the home, but like I only show like less than 1 minute.
Right. I'm just saying, proportionally, it seems like the bus was
the person is a faster walker. Really.
I want to have at least the bus seem a little faster than the walking.
Buses are slow.
There's pedestrian speeds these days.
So when you were actually recording the measurements, did you have your arm out of the bus window?
The case is here is like when you get on the bus, sometimes it's very crowded and you have no space to even sit. Then usually you have no GPS measurement. But if you have a seat there, even though you don't need to put your GPS out of the window, it still can get some measurements. Sometimes the measurement is very sparse, but it's okay. We can still track.
Can you use the sparseness as evidence?
Do we use what?
Could you use the sparseness of the data as evidence that you're in a car or a bus?
Yeah, that's a very good point. Here we didn't use that.
So we have a project in our group this summer that Rand's doing on reasoning about GPS shadows and the signal loss across that.
Yeah, we have an assumption here though is like if you have no GPS measurements for like more than 15 minutes or 10 minutes, then we assume this person is inside the building. So we have this assumption. If you have very short data loss, like 30 seconds, then it will not affect our tracking. We can still, yeah.
So if this person is on foot, then your constraint of edges being on the road is not valid anymore, right? This person can be anywhere. How do you handle that?
That's a good question. So even though we can think the user can work anywhere, but our location tracking will be like track the location of the user at the nearest edges, nearest street. So although our location tracking is not exactly correct, but we can still have a pretty good approximation. Except you walk to a very area that's no street near you, but that's very rare.
But one would imagine you could generalize this so you have the sidewalks within the UW and know that if you seem to be walking, you might be tracking the sidewalks, and that would be more evidence that you were on foot.
Yeah. So
or you could just expand your GIS, in other words.
Yes, sure. We can have more detailed.
It's a huge data acquisition issue.
GPS tracks.
But having the sidewalk information in the GIS is not true. We're about just using speed as a coarse approximation of mode. You wouldn't be able to distinguish necessarily bus from car, but you should be easily be able to say marking from bus.
Yeah, but the problem with though is like sometimes even though you're in a car, still pretty very slow. When you have a traffic jam, right? So you should consider all the information from the history. If you in the car most of the time and only on a very short time you are very slow, then it's very likely you are in a traffic jam, not just work. So using this technique, we can include all the information from the history till now. Got the most accurate estimation.
So what's the number of particles that you use in this?
In the picture, I use like about like a few hundreds, like 200 or 300.
It's actually pretty high dimensionality. What's the number of dimensions that you're having?
So we have like the first dimension is like the transportation mode.
Yeah.
The second is the velocity, and for the location we have distribution for each particle. So we know that exactly. So I can see it's like because it's only 3 or 4 dimensions. Okay, so that's not the end of our story. We still want to know more about the transportation routines. So before we move on, I first introduce some concepts using example. So in this example, the user goes from the home to the workplace. He first walks to the bus stop A. Then he takes the bus from bus stop A to B. Then he gets off the bus and walks to the workplace. So in this episode, we have a single goal, which is the workplace. In general, we can have like our home, our friend's home, restaurants, the doctors, the grocery store as our destination. And in order to go to the destination, the user may switch transportation mode. In order to model that, we introduce the concept of trip segment. So each trip segment includes a start location, an end location, and a transportation mode used during that segment. So for example, in this episode, we have 3 trip segments. The first segment is from the home to the bus stop A on foot. And the second is from bus stop A to B on bus. And the third is from B to workplace on foot. So we also want to infer the user's goal and the trip segments. To do that, we add another 2 variables to our network. So we add the goal and trip segment, and we added the dependency between them. So the question then is, how can we do the inference in that very complex hierarchical model? And the answer is still the Rao-Blackwellised particle filter. So to do that, for each particle, we add a joint distribution of the goal and the trip segment. Then I will show how we do the inference using example. So suppose at time k-1, we have the full distribution of all the variables. In order to get the estimates for time k, we first sample a particle from distribution. We get this particle as k-1, the particle I. And to infer for each particle, we want to infer the estimates for time k. To do that, we first predict the joint distribution of the goal and the trip segment based on the previous information. Then, based on the estimate predict the goal and the trip segment, we sample the transportation mode. We sample the edge and the velocity and data association, and we use the same Kalman filter as we discussed before to update the position distribution. After this step, we have the posterior distribution for transportation mode, for all the location velocity, and for data association. At the final step, we still need to propagate this low-level information backward to update the high-level information. Then, after these 3 steps, we have the full distribution for the time k. Then we can do the same thing for time k+1, time k+2, and so on. So, any questions?
So what's your dynamic model for your GK and TK? You have to predict what's GK and TK, right? Is that you assume it's constant or what?
You mean here, how do we predict the distribution of GK and TK? So your goal will basically your goal has some strong relation with your previous goal.
Yeah.
And also, your location will affect your goal. Right? If your location now is already at your previous goal, then you can switch your next goal. If your current location is not at your previous goal, then you cannot switch your goal.
But normally, when you move a particle, you need a dynamic model to let the particle move, right?
Right.
I just want to see. So here, do you have a mixed state kind of dynamics, or what kind of dynamic model that you use?
I think the dynamic model is just like what I talk about. So for the dynamic model, it's not a very regular dynamic model like you express in the function.
Right.
It's just like you can think it's some code. Like you compare your
rule-based, some rule-based.
Yes, exactly.
As you go there.
Yes. So you know your goal at time k -1. Then you compare your location with your goal. If it's the same, you can switch. If it's not the same, you cannot switch. But when you switch, you still have to sample sometimes if you want to switch or not.
So I want to understand the question and the answer better. So you're asking what dynamic model you actually used to do the transitions between k minus 1
Particle, yes, correct.
And the answer was heuristic or rule-based?
It's some rule-based, like so.
Why can't you learn that from data?
Because we use some unsupervised learning. We don't label it as
unsupervised. So it's supervised in the mind of the heuristic writer. That's the answer. So that's interesting. So it'd be interesting to compare your heuristics with some supervised training of the goal transitions.
The problem is, like, if you want supervised learning, then you need to have the user label at each time. What's your goal? What's your segment?
But there's no other way to evaluate this, right? In other words, you can evaluate it based on some test holdout data, but it would be interesting to see how much better you might do with a supervised.
Yeah. So we haven't compared our current approach with supervised learning because that's too much work for us. So we just use this simple way to do that.
Have you evaluated the methodology? We haven't evaluated in the way you said it, like to compare the accuracy or compare those. But we have the general evaluation, like if the learning result makes sense for us, if it's a tool. For example, if the goal we learn is a real goal for us, so we have those evaluation, but not like quantitatively, learn. You mean you evaluated it qualitatively by just looking at whether the results make sense or not?
Yes. We can move on. Okay, we show another quick demo. So in this demo, we want to the user drives leave the workplace, and the system wants to predict where the user is going. So these blue circles are the possible goals. So the size of the circle is proportional to the probability of the goals. Okay, now the user is drive forward, and the most likely goal is the one in the middle. Okay, at this time, when the user turns left, this information quickly propagated to the upper level, and the system changing his most likely goal is the one on the top left. And this black line are the most likely paths to the most likely goal. From here to there is around 100 blocks. So our system can predict pretty far away.
Does the model learn new goals if the user's behavior changes and suddenly he goes to a specific restaurant or whatever over time that he didn't used to? So will he learn that that's a new goal that needs to be added to the model?
So our current work only remembers the old places, so it cannot distinguish the new goals. But your work is exactly our future work. So I will talk about it in our future work. So far we have finished the inference technique, and The second part of this talk is unsupervised learning. So
before you go on, Lynn, so do you have any sense for how this methodology was either in the engineering phase of it, the heuristics generation, and the run performance, if you had like a very rich set of destinations over time, like literally hundreds? My sense is that I'm not so sure how well the supervised heuristics would do for that. It seems like the model, the studies here have been 3 or 4 places someone goes, and that's their life. Maybe we're all that boring. I'm not sure. I've done my own paths lately, but I'm concerned about scalability.
Yeah. So I think we use Rao-Blackwellised particle filter, and we keep a distribution of the goals and the true segment. The reason to do that is we want to use as few particles as possible, so to make the inference very efficient. So if you have, when you have more, so basically the complexity of our approach is increased squarely with the number of goals, number of the true segments. So you have, if you have 100 goals, basically you need like 10,000 more space around that.
Well, beyond the effectability, though, you have the issue of the performance of the heuristics to discriminate among increasing numbers of competing hypotheses for accuracy. And so I'm concerned that you'll start losing accuracy with the heuristics. If you have a lot of points potentially not scattered geometrically way apart, but closer together and so on.
Yeah. Yes, but I think that's an inherent problem. Because the human behavior are very, very uncertain in that way. But our techniques, the good thing is like, although at the beginning the systems are not certain about where you are going, because you have to go to so many places. But after you go forward for a while, we can integrate the new GPS measurement to our system, and we can predict at real time you're most likely to go.
Oh no, I think having uncertainty in there is critical, and I like that part. It's whether it's coherent or not, whether it's trained the best way you can train it or not, and so on. That's what worries me. But
I think I admit that right now our experiment is simple to be used in the engineering at this time. But I would like to use the approach for more people and more goals to test that.
So there's another thing, for particle filters, one of the experiences is to support multiple hypotheses. But by looking at your experiments, most of the particles are centered around a single mode, meaning it's more like a single hypothesis thing going on. So I'm not sure when you do the resampling, do you actually give some probabilities to some other places, even though their probability is low? But it looks to me you are not doing that.
So that's a very detailed question. So the answer is like this. So because we keep a joint distribution of the goals and uncertainty, so even though some goals are very low, it still has some values in the distribution. For your transportation modes, because we sum transportation modes, right? So each particle can only have one transportation mode. The thing we did here is like we only show the particles with significantly high weights. So there are still many particles that cannot be displayed here with very low weight, but it can also capture the other transportation modes.
Actually, it'd be nice if you show those particles as well. Then people will see how that evolved.
So the reason is like we use a very special resampling. We sample the particles within each mode. You can see like we have a weight of how basically you can see we have distribution of the transportation mode, like how many particles should be car, should be bus, should be foot. Then we resample them within that each mode. It's a very special resampling, so we didn't show that. Maybe we can discuss more later offline. So the model learning is key if we want to predict the user goals and to detect user errors. So we have two preferences. We want the model to be customized for each user. Second, we prefer the unsupervised learning because then we don't have to let the user to label, so many training data. So the training data here we use is 30 days GPS reading of one user only, and we don't have to label the data at all. It's just like raw GPS reading. So remember, this is our hierarchical model. So given the user, we don't know what are the possible goals for that user, and what are the possible chip segments for that user. So the first thing we want to learn is we want to learn the domains of the goal and the chip segment. To learn that, we use some heuristic. So basically what we did is we use EM learning on a flat model. So the flat model is just our hierarchical model without any high-level information. Then we do the EM learning. To be more specific, we first track the user forward. Then we reverse all the GPS measurements and we track the user backward. And we combine the statistics from the forward path and the backward path. Then based on the combined statistics, we find those locations where the user stays for long periods of time. And then we regard those locations as the goals. Second, we find those locations with very high mode transition probabilities. Those locations can be bus stops or parking lots. So after we inferred those mostly frequently used bus stops or parking lots, we can know what are the possible chip segments the user will take. Here is the learning result using the 30 days training data. You can see from this experiment successfully extract 6 most likely goals, most significant goals. So the workplace, the home, the grocery store, and the 3 friends at home. Also, it can identify the most frequently used bus stops, shown in the green circle, and the parking lots around this area. So after we learn the variable domains, we also want to learn the transition matrices between the goals, between the chip segments. So to do that, we use another EM learning on the hierarchical model. This EM learning can simultaneously estimate the transition matrix between the goals, the transition matrix between the chip segments given the goal, and the transition matrix between the streets given the chip segment. So here we visualize the result of the learning. So on the left picture, we show the area near the workplace. And the goal now is the workplace. And we show different chip segments to the workplace. And for each chip segment, we connect the very likely street transitions. From here, you can see how the user go to the workplace through different transportation modes. So for example, you can see here, the user first drives to this parking lot, then walks to the workplace. At this place, you can see the user first takes the bus to this bus stop, and then they walk to the workplace. So on the right picture, we show the same area, but the condition on a different goal. At this time, the goal is going home. So from the picture, you can see how the user goes from the workplace to the home through different transportation modes. After we talk about the inference and learning, I will also briefly talk about how to detect atypical behavior. So this detecting atypical behavior is essential if we want to help people from suffering from Alzheimer's diseases. In this paper, we use a technique of model selection. To be more specific, we run 2 trackers simultaneously. So the first tracker assumes this person is doing something normal. Then it uses the learned hierarchical model. And the second tracker assumes this person is doing something very atypical. Then he just uses the untrained flat model. And at each time, we estimate the likelihood of each tracker given the observations we have. So if the user is doing something normal, then the first tracker will have a higher likelihood. On the other hand, if the person is doing something atypical, then the second tracker will have a higher likelihood. I will show this idea using another animation. So in this animation, the user goes from the workplace to home, but he missed the user bus stop here. And we use the bar to display the likelihood of both trackers. So the red bar is the likelihood of the atypical tracker, and the black bar is the likelihood of the normal tracker. So, and here the user wait at the bus stop, okay, get on the bus, move on. Because this route is already well learned. So at this time, you can see the probability of being normal is very high, close to 1. But at this place, the person missed the bus stop. Then you can see the probability of being abnormal jumps up very quickly. And the system knows, okay, this person might do something atypical. So our previous approach of model selection is simple and very effective, but it cannot distinguish user errors from intended novel behavior, because those user errors and intended novel behavior will be regarded as atypical. So how to distinguish these two? In order to do that, we can combine our inference with the user's input and calendar information and so on. So to show how it works, we show an application called opportunity knocks.
Have you done that last step yet, or you saying that's a solution for the future? The last step, have you done that?
You mean?
The solution.
This solution, yes. We combine it with user's inputs. You can see in this.
Demo, okay.
It's not in the original paper, but this is another paper published in Urbicon this year.
Right.
It's not in the AAAI paper. So the system of opportunity knocks include a client side and a server side. So the client side includes a cell phone and a GPS receiver. The cell phone can transmit the GPS measurements to a server, remote server. So on that server, we run our learning engine and inference engine. And the server can transmit the inference result back to the cell phone. So in this episode, a senior person carries our cell phone, and when he leaves the workplace, he asks the system display, the cell phone display the 4 most likely goals of the user based on the previous experience. Then using the pictures, then the user clicks the first picture, indicates he wants to go home. Then our inference engine will instantiate at the back end that now the goal is the home. And but the system is still not. The system does not know whether the user wants to take a bus or take a car. So it asks the user, "Do you like to take a bus or a car?" And the user clicks the bus. At this time, combined with all these user inputs, the system knows exactly how the user should go home. It displays the detailed instruction for the user. But unfortunately, the user takes the wrong bus. At the beginning, the route of the wrong bus coincides with the route of the correct bus. So the system cannot distinguish. But at this point, when the wrong bus turns left and deviates from the true route, the probability of making an error jumps up quickly. And at this time, the system realizes the user might make a mistake. So it makes some noise, like knock, 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 and display an error message here on the cell phone. So then the user realized he made a mistake, and he got off the bus. And at this time, our system can use the real-time bus planner to guide the user back home.
Does the graphs tend to look like the one you're showing, or is this poor cognitively disabled person dealing with a bunch of false positive and false negative knocks? False positive ones are more disturbing. Do we know yet? Even simple test runs, if if we have over knocking, positive knocking?
Yeah, this is like a, this is a, in this experiment, what we did is we collect the real data, real GPS data, but we do it offline.
Right.
It's not an online experiment yet. So we haven't used it for a lot of people yet. So we cannot say how disturbing it is.
I'm just saying because I think the false positives for a disabled person can be as bad as being on the wrong bus. That's just like getting off. So someone gets off the right bus and gets onto the,
Yes, but
picks them up on the corner of Main and Fifth because they hit the wrong knocking at the wrong time.
But the other information we can imagine is like we can use the real time the bus location for our inference. So if the location of the user is very different from the the real time bus location, then we can see maybe.
Well, I mean, I think in some ways deterministic. I imagine people like this have a limited scope of activities, and so deterministic, treating these bus routes like rails. You're either off the rail or on the rail, and you knock when you're off the rail. Probably might be better than managing false positives, but you look at what real performance would be, the real ROC curve.
Okay, so that's basically the talk. So there are a bunch of related work. So the Bowie and his colleagues developed the so-called abstract hidden mark model, and their model is very similar to our hierarchical model, and we borrowed their inference techniques of Rao-Blackwellised particle filter. Then there are many research on using GPS to learn significant locations, such as the people at MSR and some people from Texas. Then another interesting fact is that we also use this same technique of the tracking, graph-based tracking for the indoor case. So in that case, given the indoor map, we can extract the so-called Voronoi graph. Then we can do a very similar tracking on the Voronoi graph of the location. This is another paper at Errors. So in summary, first task, in infer location and transportation mode, we utilize many knowledge of street map, the bus route, and so on, and we combine the particle filter and the Kalman filter for efficiency. Also, to predict goal and path, we developed a hierarchical model, and we can learn those transportation routines in an unsupervised manner. Also, we can do the inference using Rao-Blackwellised particle filter. So to detect atypical behavior, we can use model selection and combine with user input or other information source. There are a bunch of maybe future work. This is the one I'm now doing at UW. So in our previous approach, we cannot detect new places. So for example, in this example, in the training data, so our system can identify the places where the user spent long periods of time. Okay, and we can ask the user to label those places as shown in this blue circle. So we have restaurant, the workplace, the gym, the grocery store, and so on. But after the training, when the user goes to the new place, our system can know, okay, now this person goes to a new place, but it has nothing to do. It cannot do nothing. It cannot do anything because it has no information in the training data. So what we want to do is we want to identify the types of new places. So we want to know, okay, this place is a restaurant. This place is a grocery store, very likely. So how to do that? The first way to do that, we can think this problem as a classification problem. Then we know this place, and we know when the user goes to that place, how long the user stays there, and where does the user travel from this place to the new place, and where the user goes after he leaves the new place. After we collect all the information, we try to classify the types of the places based on all this information. And we can learn the model based on the training data, on the labels that the user labeled in the training data. And we can identify the new places. This is one direction. The second direction is maybe we can go to map point and ask map point what are the possible business around this area. Then the problem of this is like maybe a bunch of business will come up, right? And it's hard to decide. So a more interesting research maybe like how do we combine these two approaches? The one approach is from the map, the knowledge base. Another information is from the habits of the user. So we can learn from the training data. Then it's possible that after we combine these two approaches, we can get a better accuracy. Another problem of our previous work is we require for each user long periods of time for training. So in practice, sometimes it's hard to get the training data for a given user. So can we generalize from the people we know to new people? So to be more specific, suppose in the training database, we have the training data for user 1, 2, and 3. But we don't have any training data for the new user. Then can we recognize some behavior of the new user based on training data from other users? We think this might be possible. The approach is we are trying to learn a general model. This general model is very different from the customized model. So we can learn a general model using all the training data we have from other people. Then we can use the general model to identify the new user behavior. As you can imagine that this general model cannot do as accurate as the customized model. But we think it can maybe identify some of the behavior of the user. It can provide some help. Then after the new user have more training data, have more data come in, we can integrate the new user's data to the general model and get a customized model for that user to improve the accuracy. So the research problem is how shall we combine the training data from different users? And how can we combine the data of the new user to our general model? So all of these are our future work. Okay, I think that's it. Any questions?
Thanks. Any other questions or comments?
I have a question. You mentioned that you do the processing on the server offline.
Mm-hmm.
I assume just for convenience purposes. Do you ever feel would it be possible to do this on a mobile device, like a pocket PC?
Yeah, I think it's possible. In fact, we have developed a real device using a GPS, using a GPS receiver and a cell phone. But the demo I show here is do offline, but we can do it online.
Okay.
There's no difficulty, I think.
Okay. Thanks very much.
Okay, thank you for coming.